Today, we have the pleasure of having Mariel Saez from PUC in Chile, who will talk to us about eigenvalue bounds for the Paneitz operator and its associated third-order boundary operator on locally conformally flat manifolds. So, Mariel, the floor is yours. It's when you want.
Thank you very much. Thank you very much for the invitations. Actually, this is one of the good things, I guess, about these virtual meetings, that you can be anywhere in the world, any day of the week. I'm very excited, actually, about talking in this seminar with experts on eigenvalues and to hear your views on this work. That is joined with Maria del Mar Gonzalez. She's in Universidad Autónoma in Spain at the moment. And I want to start a little bit with the motivation that we had for doing this work. That comes from the two-dimensional setting. I mean, you all know that eigenvalues have a big connection with geometry, but in 2 dimensions in particular, there's a very strong connection also between geometry and topology. So this carries out to the eigenvalues of, in particular, the Laplace operator. And some of the results that existed in that setting, it was the sort of starting point for what we started looking at. Two things that are very important when you get these bounds, maybe not precisely stated in this form, are the uniformization theorem and Gauss-Bonnet theorem. That they're going to appear also in my talk later. And I want to remind you about a bound that you have for eigenvalues of the Laplacian in the two-dimensional setting that is written there. That here my chi1 or whatever that letter is the first eigenvalue of the Laplacian. I'm thinking n to be a closed two-dimensional manifold. And then you can bound that eigenvalue in terms of the times the area, because that's the scaling invariant quantity, in terms of the genus of the surface. And this is actually sharp in the case of a flat disk. So when gamma is 0. And this kind of result has been studied by many people. I think this particular bound was done by Yang and Yao, but then there are many authors that worked in similar bounds, in similar settings, if you have like a Neumann boundary condition, or trying to generalize for higher dimensions. And so sort of this goes a little bit in that direction. So how can you generalize in higher dimensions when it's not even clear what would be the topological invariance that would enter into this inequality? In 2 dimensions, somehow this is a bit easier. And something that is very important when you look at the proofs of these kind of results is that in 2 dimensions, you know, and this is basically comes from the uniformization theorem, that you have a conformal embedding into a subset of S2. And you use that embedding to get this kind of bound. And the other thing that you will see when you look at the proofs is that the Laplacian is a conformal operator. So these are two very important features of the proofs of all these types of results. That the conformality of the operator, and the fact that you have an embedding into a model that you know how to compute things. I mean, this basically is the idea behind. So we were trying to see in other dimensions, I mean, in principle, what we were trying to look at, if you have a conformal operator, how much can you carry out the theory? This is a little bit of what Li Yao do, for instance. But what if we change the operator? What if we have different kinds of operators? And in particular, we started with like the next sort of generalization of the Gauss-Bonnet formula, that you can prove it in any even dimension, in particular in 4 dimensions. And in 4 dimensions, you get that formula there. You have 2 curvature quantities here, the Weis tensor. That is something that doesn't make sense in the 2-dimensional setting, so it won't appear there, but it's something that is conformally invariant pointwise. And the Q curvature, that is something that is not conformally invariant in itself, but the full integral of it, given that is equal to a topological quantity, has to be a conformal invariant. So the total Q curvature is a conformal invariant, and the Q curvature is written down there. Is up to the leading order is a Laplacian of a curvature, so it's a 4th order type of curvature quantity. So it has 4 derivatives, and also can be associated to a differential operator that is the Paneitz operator. And the Paneitz operator is what I tried to write down here. That if you look at it, this is the Paneitz operator in 4D. If you look at it in more dimensions, you have extra terms. But in 4 dimensions is this thing here that has as leading order the bi-Laplacian. So you have 4 derivatives. And then you have a lower order term that sort of carries out the geometry that you're going to have in there. So what we were thinking about when we started thinking about this, I mean, here there's a more precise definition of what the other quantities are that are relevant if you want to compute things. But what we started thinking about here is, what about the eigenvalues for this quantity in 4 dimensions that clearly has some connection with topology, at least through the Q curvature. The Paneitz operator is going to tell you how the Q curvature changes under conformal changes of metric. The Paneitz operator is a conformal operator in the sense that if you take a multiple of the metric, you're going to get a multiple of the operator. And these were kind of the elements that we saw in the proofs in the 2-dimensional setting. So the question is, how much of that can be carried out here, and what would be the topological quantities that you see when you do that? But there are a few factors on the operator that the Laplacian doesn't have. One thing is that the operator is not necessarily positive. The other thing is that in general, you don't have topological classification in this case. Not everything is, you don't have a geometrization in this case, so not everything is associated to a certain geometry, but you have certain situations in which you can sort of address these issues. There are situations in which you know Paneitz is positive, and there are situations in which you know how to classify in terms of the total Q curvature. I mean, actually the road is a little bit sort of described there, that if you can have constant Q curvature, in some cases you can classify, and there in those situations you can also solve what is called the Q Yamabe problem. That is basically you can find a conformal metric that has constant Q curvature, and in that case you can classify. So some of the restrictions in the theorems that I'm going to present today come from these facts, that we need to study something that has at least a lower bound on the first eigenvalue. So we're going to restrict ourselves to the case that P is positive, and in which we have some sort of known classification for the topology. So let me show you the first result, and then I'm going to comment a little bit on the hypothesis, but the motivation behind is sort of here, in the fact that we need to address these issues here. So this is the first theorem. I don't know if it's big enough. We're talking about compact manifolds, orientable, closed, and locally conformally flat. This hypothesis here is one of the things that I didn't comment before, but it's related to the fact, one of the key points that I marked in the 2-dimensional case. In 2 dimensions, you always know that you can map into S2. In 4 dimensions, this is not always true. And the locally conformally flat condition is sort of replacing that fact. So if we assume that you're in the locally conformally flat case, then you know that you have a mapping into S4. In principle, locally conformally flat only tells you that you have a local mapping, but in the work of Shen and Yao, they show that you can extend this to a full map to S4. I mean, you have a global map from M to S4. Although that map, that is called the developing map, in general, it's not going to be injective. So somehow we gain the fact that we can be immersed into S4, but you have to address it. I mean, we have somehow to take care of the fact that that thing might not be injective, or at least try to see under which conditions we have something that is injective, and we can really compare with the models that we know how to compute things. So that's the hypothesis there. And then we have 3 results here. In reality, the first one is something that, well, the first one and the second basically take from facts that were already known. The topological classification that is described there was already known from before. And our contribution here is sort of from that classification, what can you say about the eigenvalues of the Paneitz operator? So in the first setting, we're assuming that it's simply connected, and then it's known that it's conformally equivalent to S4. And in that setting, basically what that inequality says is that under that condition, you can compare with the first eigenvalue for the Paneitz operator on S4. The second hypothesis, I didn't even completely define the quantities that appear there, so I want to comment on them. There are two things appearing there. The first one is the Yamabe invariant, and that is another conformal invariant that is defined as follows. So the Yamabe invariant is what you use to solve the Yamabe problem, and it's the infimum of the integral of I don't even know what I wrote here, but okay. So it's the integral of this, and here I'm gonna get the power wrong for sure. Yeah, I know what I wrote. So this is the integral, sorry, of the scalar curvature divided by the volume, and here's where I'm gonna make a mistake for sure, but I think the power here is 1/2. And this is over matrix G of F, and the volume G of F, where G of F is e to the F and some background metric 0, G0. So basically, let me say what I'm doing here. This is the quantity that you try to minimize when you solve the Yamabe problem. And if you find that infimum, that metric is going to have constant scalar curvature, and it's going to tell you something about the topology of the manifold in certain cases. In particular, in the locally conformally flat case, these are classified, and that's what that thing there is saying. And KG is something that I should have defined. I'm sorry, this is just the total Q curvature. So basically, these two conditions there, what they're telling us is that you're going to have that the Paneitz operator is positive, and in the setting of Yamabe positive and Q curvature positive, there is topological classification. So maybe I should go back to the theorem. So this is the two parts in there, and the third part is in the case that the total Q curvature is 0, and in that case, what our result is saying is that you're inside a piece of a cylinder, and we are using this maybe in a slightly different way than the other two results, but the ideas are basically the same, to obtain bounds on the eigenvalue using this, this mapping into this cylinder kind of region. Okay, so these are the results in the closed case. In this case, maybe, as I said, like the first and second one were kind of known in the community. They were maybe not written in this exact form anywhere, but they were sort of known. And what we were really interested to start with was more in the boundary value problem, because, you know, like there is this very interesting result in the two-dimensional case. There are all these very interesting results about the Spectral eigenvalue problem. That would be our two-dimensional analog for the boundary value problem that I'm going to present in a minute. In the two-dimensional setting, you have the Dirichlet to Neumann map. Basically, what you do is you solve, you find a harmonic function with a certain boundary value, and then you take the Neumann value, so the normal derivative of your solution, and that is called the Dirichlet to Neumann map. The eigenvalues of that are usually what they're called the Steklov eigenvalues, that are very well known by many of the people in the audience from what I see here, much better than me for sure. And then in the two-dimensional setting, again, you have a very nice result in terms of the topology of the domain. And that relates the first eigenvalue with the genus and the number of boundary components. And this problem has been studied for a long time, not only for the first eigenvalue, there are results for all eigenvalues. I'm here only stating the first one because I'm only going to refer to the first one in the case of Paneitz. And there is known that if you have, for instance, one boundary component, this inequality is sharp. That was obtained by Weinstock many years ago. It's attained at the flat disk. And when you have two boundary values, there's a series of papers by Fraser and Shane that they try to understand the problem with two boundary values, and they develop a very nice theory relating to minimal surface, free boundary minimal surfaces. And there are very explicit computations there that were one of the inspirations for one of the results here. Actually, one of the first computations that we did is try to see if for Paneitz we could have results that were similar to them and maybe relate to some kind of not minimal surface, but maybe some other kind of surfaces. But actually this was not so very successful because the computations, although they're kind of elemental, they're very complicated, and so it was very hard to see anything on the computations. I'll comment on this in a minute. So this is the kind of thing that we are trying to generalize. Then, of course, there is the natural question of what would be the boundary operator in this case. The Dirichlet to Neumann map is something very natural because we know that these are the boundary conditions that we can pose for the Laplacian in general. But Paneitz being a fourth order operator, you need more boundary conditions. And the question is not only that, because in this case, in the case of the Dirichlet to Neumann map, in fact, the conformal property in 2 dimensions is inherited by the operator from the Laplacian. So we want to understand, in the case of Paneitz, what are the natural boundary operators that are conformal as well. So sort of to try to extend this part of the theory. So let me tell you, some of them don't look that nice. So I'm going to describe what the boundary operators here are. Here you have 3 boundary operators that are natural. The first one, this, I changed my notation here, but this is the normal derivative. I mean, this you can understand just as the eta of u. And I think actually there's a minus that are missing, and there should be a minus depending on what your normal is, of course. But you have that one, then you have a order 2 boundary value operator, and an order 3 that is this long thing that I wrote down there that I couldn't find a better way to fit it on the screen. Sorry, because it's kind of big, but I hope it's visible. And as in the case of the Laplacian, these these boundary operators come from integration by parts, basically. If you take your Paneitz operator and you integrate it by parts, what you're going to see at the boundary is basically something of the form of this energy of this bilinear form that I have there. So, and each of them is conformal of order the subscript that they have. So B1 is conformal of order 1, B2 is conformal of order 2, and B3 is conformal of order 3. And the third one is the one that we're gonna study in a particular setting as well, because as Paneitz is not positive, this might not be positive as well. So we are gonna need conditions for this thing to be positive. And again, we're gonna go into the locally conformally flat case. That is where we know that we can compare with sort of a known model, or we have a little bit more information in that case. This operator is also natural from the geometric point of view, because in this setting, you also have a curvature quantity that appears in the Gauss-Bonnet formula when you add the boundary, and that curvature quantity is a T curvature. And it appears in the Gauss-Bonnet formula with boundary in this form as the geodesic curvature appears in the 2-dimensional setting. So this is gonna be Gauss-Bonnet in 4 dimensions with boundary. And basically the T that appears in there is related to B3 in the same way that Q is related to P. So I mean, if you want to have a connection between geometry and topology, these seem to be sort of natural operators for that. And that was sort of the inspiration of why we chose that. Although, as you saw in my previous theorem, we cannot really exactly relate our formula to these quantities yet, or to the, I don't know, to the topological invariants that are involved in all these things. So that is sort of the base of the theorems that I'm gonna prove today. There are basically two main theorems and a corollary. The problem that we're gonna study is basically you associate to the boundary certain function u, and you solve the Neumann problem, Paneitz equal to 0, and then the operator here is given by B3, and it's a relation between B3 and B2, and the eigenvalue problem is gonna look like this. Basically, we're gonna be studying that equation that appears in here, and for that kind of lambdas that I wrote in there are the results that we're gonna try to find. I mean, we're gonna show that it's a positive operator and the hypothesis that we're assuming, and that we can find bounds. We can find uniform bounds that are again based on the fact that if you are in a suitable setting, basically you can sort of find conformal models that are related to the manifold that are going to give you a geometric bound. So let me again quickly go over the theorems here that we're going to address. I'm basically going to prove 1 and 4. I mean, 1.3 is just saying that these conditions sort of carry from the previous theorem, and that we're not going to have negative eigenvalues. We're only going to have positive eigenvalues, and the 0 eigenvalue is only associated to constants. Yeah. So the first theorem is a topological classification, and the last theorem is using that classification to get bounds on the eigenvalues. So basically what I'm saying here is that if you're simply connected and have one boundary component, then necessarily you're conformally equivalent to a half sphere. This was, again, sort of known in a different setting. It's in the thesis, at least, of a student, Spiegel. There's no paper. I mean, there's a paper on arXiv, but it was never published. But that result was known before. The second one, you see that there's a number in there, and that's because it was also known in this case that under those conditions, being not necessarily simply connected, but you have Euler characteristic 1 and Yamabe positive, then you also have sphere. I'm cheating a little bit here because the Yamabe invariant in this setting is not exactly the same as before, because you have a boundary, so you need to add a boundary term. And I'm going to avoid talking about that because I'm not gonna need it in what I'm gonna show, but just to remark that the Yamabe invariant with boundary is not exactly the same as the one without boundary, but you can still write that. I'm gonna mention it briefly later on. And then we also wanted to address, as I said before, the case with two components, because this is sort of mimicking in some sense the work of Fraser-Shane. Very little of it we could carry on, but I mean, that was sort of one of the inspirations that we had when we were looking at this. That is the case with two boundary components. We're going to assume that these boundary components are umbilical, and I didn't mention in the two previous ones, we're also assuming that they're umbilical. The reason, well, one reason for assuming this is that this, in some sense, simplifies lots of computations, and it's a conformally invariant property. So it's a natural one to assume if you want to assume something about the boundary. Some of the things I'm not sure you can carry out without this assumption. Basically, with this condition, what we're saying is that the model is given by an annulus. I mean, that if you have something that is simply connected with two boundary components, positive scalar curvature and positive Q curvature, then you're necessarily an annulus on R4. And then we can use that model to find bounds on the eigenvalues. So part of this work actually was to do computations explicitly on these models on the half sphere. This again was kind of simpler and kind of known. And then on the annulus, the computations on the annulus, they're not hard from the theoretical point of view, but they're not very nice actually to perform. So although we could get some values, I mean, we cannot even say in general what is the smallest eigenvalue, because we know that, I mean, we computed a series of eigenvalues, and we know that in some situations it's given by the ones with the first spherical harmonic, and in other situations by the second one. And we cannot, in the case of Fraser chain, they do exactly the same description, and they can describe when this changes, and that in that point you have that actually you have 3 of them being equal, and all this kind of thing. In our case, we kind of suspect that this is the same, but we could not compute it. I mean, the computation was just too messy, and we couldn't find a way of seeing this. So we can just, the boundary, all of this is to say that that's why the boundary is sort of explicit, but we don't, it's not optimal. We don't know the optimal bound even in the model case. So, I mean, we don't know if this, what would be the optimal thing in general, but certainly depends on the row. I mean, certainly depends on the ratio of the 2 radius in general. I mean, you can scale this and it's the same. So yeah, so having said that, I mean, I want to talk a little bit about the proofs, but I don't know if anyone has any questions, because I usually, when I had written everything, I tend to go too fast. So
I actually have a question. It's Alexandre here.
Sorry?
So I have a question here.
Yeah,
if you don't have conditions to have lambda 0 equals 0, you will have a finite number of negative eigenvalues, right?
Not necessarily. I mean, you could have them all going all the way to minus infinity, I think. Okay. Yeah. I don't think you have a lower bound in general.
So the operator becomes unbounded below the operator?
Yeah, it could be, yeah.
Okay, thank you.
I also have a question, if you don't mind, before we go to proof. So you mentioned this connection to minimal surfaces with Fraser chain had. Have you tried doing similar computation here?
Yeah, we tried, but we were not super successful. I mean, it's certainly something that would involve minimizing mean curvature, but you have extra terms, and we don't know what those mean in general.
Have you tried doing it in a closed case? Maybe it's clearer there.
Yeah, I mean, I mean, yes, but the answer is we couldn't really see exactly what would be the natural quantity to minimize. Because, I mean, it's second order, right? So, I mean, yeah. I mean, mean curvature is kind of a natural one, but it's not so clear that just minimize. I mean, this would be like a Wilmore surface in some sense, right? But it's not clear that it's exactly that.
Okay, thank you.
Thank you. That's a very good question, though. Any other questions or comments? Or, I mean, otherwise I'll go with the proofs a little bit and try to explain the ideas behind the proofs. As I said, my first theorem, theorem 1.1, the one on the closed case and the case without boundary. The first 2 cases are more or less known. And basically, everything comes, as in the 2-dimensional case, from the fact that you have an energy here, that the eigenvalue can be characterized in a variational way. This is the energy that you have. And under the conditions that we have, this energy is positive. As you see, this second term in principle is something that doesn't have a sign. And that comes from, I mean, the question that you were asking before, that this second term actually can be in principle whatever, but in the conditions that we have, I mean, there are other people that have studied when can you say that the operator is positive. We will have that, in fact, the infimum is attained. Well, you have always you have the zero eigenvalue, but it's only attained by constants, and then all the other eigenvalues are going to be strictly positive. So in the first case that I had, let me remind you quickly what the theorem was. We have that it's simply connected and closed and locally conformally flat. And there is a result by Kuiper that states exactly that in this setting, you are conformally equivalent to S. I mean, in any dimension, in fact, you're conformally equivalent to Sn, and we're in 4 dimensions, we're conformally equivalent to S4. So for the first one, we are basically using a known result that M is conformally equivalent to S4. Equivalent to S4. And then you have an embedding. Then you have a phi that goes from M to S4 that is conformal. And here we use the same idea that Yang Yao or any of these, or many of these authors, I don't know all of them, but many of them use, that we use the coordinates as test functions of on the energy. Functions on the energy. And since we're on the sphere, we also have that the sum of the squares of these is 1. So basically, you can just plug into the energy and see that lambda 1 is going to be, this is just a 1, less or equal than the integral of, let me write it like this, of the energy in S4, basically. The energy of phi, in principle in M, but because this is a conformal embedding and the energy is conformal, this is the same as computing the energy on S4, actually. Here we're using the conformal property. And this is something that you can compute explicitly. And I'm missing the sums, I'm sorry. I mean, here you have a sum on I, and here you have a sum on I. And this is something that you can compute explicitly. And actually in the paper that is posted on arXiv, we have to upload a new version. There's a mistake on that computation. The number is wrong. The idea is correct, but the number is wrong. And it's 64 pi squared. It's something that you can compute explicitly. And yeah, I mean, this is just it. And basically it's the same idea of what you do in 2 dimensions.
Can I quickly ask, can you scroll to the energy?
Yeah, I can scroll to the energy.
So is this a natural quantity in any, for you have this middle term, which is sum of energies of phi I. So is that an sort of natural energy associated to a map to a sphere?
Yeah, well, in the case of the sphere, because everything is sort of diagonal, I mean, basically the eigenvalues are the same as the eigenvalues of the Laplacian. I mean, the second term is just the energy of the Laplacian. So basically you have a Laplacian square and the other one is a multiple of gradient U square.
I'm asking more generally. So suppose you have some map from manifold to the sphere.
Yeah.
And you can write down this expression, sum of phi i's.
Yeah.
Is that some sort of energy that is considered and for the problems, which is a natural from any viewpoint? You know, like if you do the same thing for the surfaces, right? What you get the Dirichlet energy and I think you can points and harmonic maps, and that's interesting to study by itself.
Yeah, no, I mean, yeah, I know what you mean. I don't think I've seen it done in more general cases. I mean, no,
so
I think it's natural, but I don't think anyone has done it. Maybe this is the answer. Okay. But I think it's kind of a natural thing, and that's sort of what we're looking for in some sense at the beginning. Try to see if we can have some sort of natural mapping into something that you can understand better, I mean, in some sense. Yeah.
Right, so I don't know what these things are that people study, some things called biharmonic or like higher order harmonic. This is not it, right? You're saying it's just
this is not it, but it should be related. I mean, if you are in Rn, this is exactly a biharmonic function, and yeah, I don't know if this is a biharmonic energy. This is a good question, but I know it's related, but I don't think it's exactly the same. I mean, certainly the terms that you have, I mean, okay, let me say it in a different way. The terms that you have in the second part in this formula are written in an intrinsic way, and when you do biharmonic maps, the terms that appear are all extrinsic because it's how you embed into a certain other manifold. And yeah, there's a connection between these two things, but I don't know if what you get is exactly the same thing. So maybe, but I don't know. But that's a good point, yeah.
Okay.
Yeah, so in biharmonic maps, whatever you see there are terms of the embedding, and here these are like the intrinsic quantities of the manifold. Yeah, so let me say something about the other two cases, because there's more here. And it's where you see the Gauss-Bonnet theorem and the reason why I mentioned it. The other two cases. One of my assumptions is that the integral of Q was positive, and one was strictly positive and the other one was 0. So from Gauss-Bonnet, what you get from that is that the Euler characteristic has to be positive. And you're using here Gauss-Bonnet, but you're also using that it's locally conformally flat, because when you're locally conformally flat, the Weil tensor that appear also in my Gauss-Bonnet formulas is 0. So that's not in there. It's just integral of Q is equal to a multiple of chi. And then the Euler characteristic, that's the word, sorry, of the Euler characteristic. These kind of things were classified, actually, things with positive Euler characteristic. And the following is known. If you have Yamabe positive, that was my other condition. If you have that the Yamabe invariant is non-negative, let's say, you could have, or you would have that the Euler characteristic is less or equal than 2, and this is an integer. So basically you have three cases. You have that is 2, 1, or 0. Or 0, I'm going to put it here. In the case that is 2, it's known that it's a sphere. In the case that is 1, it's known that it's a projective plane. So it's non-orientable. In particular, we are not going to deal with this case because we assume that our surface is orientable. And the more rich class is in this last case, that you don't know exactly what it is, but it's a quotient of the cylinder. It's a quotient of R cross S3.
Yes, sorry, please, I have a question.
Yeah.
In fact, you said that when Y is positive, then the Euler characteristic is less than 2. How it comes, this fact?
This is a work of Matt Gursky in dimension 4. This is not general, This is in dimension 4 and 6, actually. And he shows that if you have Q positive and Yamabe positive, these are the only possibilities, and it's a long paper on that.
Okay.
Yeah, and
okay,
he does all this topological classification. So actually, this I should mention, this is Gursky. This is actually 2 papers of Gursky. So it's not a simple result. Yeah. So in the first case, when the Yamabe is, when chi is 2, the Yamabe is strictly positive, and we know that we're in the sphere case, and it's the same case as before. And in the last case, you know that you're a quotient of the cylinder, so you're not exactly a cylinder. But you know that you have an embedding, a mapping that goes into some fundamental domain that is included in a strip of the cylinder. And this is what we're using in the last part of that theorem to bound, because basically we're going to have a mapping that is going to go from M to some fundamental domain that is going to be included in some 0 row cross S3. And now we're going to have that our mapping is going to have 4 components. And we're going to do exactly the same computation that we did before, but we're only going to consider the 3 last components. And then this is going to work exactly as in the other cases, but our bound is not going to be sharp in general. This is not, it's not necessarily, it's kind of a bad bound in general. So here we go, same as before. I want to see, check the time as before, but with the last three components of phi. The classification of these types of manifolds is not complete. And actually there are many things in here, I think. And this is gonna appear again in the boundary case. In the case with two boundaries, we're again gonna see something like this. I mean, we're gonna be again some sort of quotient of the cylinder. I'm not gonna talk about this directly in that way, but in some sense, this is some the covering of that. Is still gonna be like a cylinder, so you're still gonna see a row in there. I have only 10 minutes left, I mean, and the last two theorems, so I want to give some ideas on how you go about these last two theorems and how you go about the classification. Again, you have a variational problem. Again, you have an energy. The energy is not as nice as before. It's this long thing here. But at the end, in the things that we're gonna embed into, some things are going to be zero here. I mean, so the computation in the explicit models is actually not, I mean, we didn't do it with the energy, we did explicitly computing eigenvalues for radially symmetric functions. So although the energy is in there and I'm going to use it to compare, at the end, I'm not going to compute anything with the energy for the models. I mean, maybe for the half sphere is easier because in the half sphere that two last terms are actually zero. So I mean, it's more or less the same computation that we had before. But even that we didn't do like that. I mean, we directly computed on the models, assuming that we have a decomposition on the spherical harmonics. Okay, so let me just give you a few elements of the proofs in this case, in the case with boundary. So the first key ingredient that you have here is the developing map. The developing map is something that you can define for anything that is locally conformally flat. Is a map that goes from any M that is locally conformally flat. And if this is 4-dimensional, it's going to go into S4. And the developing map may have two issues. I mean, one of the things is it may not be injective. It's not injective in general. And the other thing is that, in principle, the image can have branching points on it. I mean, can have points where the metric is not smooth. And somehow, if you want to compare with like these given models, you want to see that you're injective, because somehow I want to be computing exactly on the model, and you want to rule out branching points. And a lot of the work of Shen Yao, it's about understanding situations in which the developing map is injective. And some of the things that we do are sort of closer, I mean, are close to their case. They usually don't care too much about the boundary case. So you cannot usually use directly the results because they're always thinking about closed manifolds, but many of the things are gonna carry out. So this is the first ingredient. And the second ingredient that is going to appear here is what is called doubling. So the idea is the following. I mean, if you have any manifold with boundary, and this doesn't matter the number of boundary components, then what you do basically is you copy your manifold and you identify the boundaries. And if you have like more than one boundary, like I'm gonna do like a not very good picture. You identify this with this, and you identify the other boundary with the other boundary. And the reason why you do this is this is a way of creating a closed manifold. And if you have a boundary, a metric at the boundary that is good enough, this is gonna glue well, and you're gonna have something that is closed. And then you can go to results as the one I mentioned before by Shen Yao, for instance. And then you can try to see that the developing map it's injective, for instance, and then you restrict again to your part. But let me tell you how then like all the other hypotheses go into the proofs. So in the case of one boundary component, then I mean you can do this doubling, and because we are assuming that the boundary is umbilic, the fact that it's umbilic means that you are mapping into something that is umbilic, the boundary. implies that the image is umbilic as well. The image through the developing map. Given that, when you know that it's umbilic, you can perform a Möbius transformation and you can transform it into a great circle. So you can take it to a great circle, to a diameter. That means that that's something that has mean curvature 0. So when you do the doubling, the metric that you're going to have is going to be smooth. It's something that is going to be nice again. And then you can sort of use, as in the case of one boundary component, you can use just a symmetry argument to see that exactly your image has to be, in that case, when you're taking your boundary to the hemisphere, then you have to be the upper or the lower hemisphere. This is enough in the one-dimensional case, and as I said before, this appears in the thesis of Fabian Spiegel, where he was studying something different. But he already argues about this construction, and there are other people, I think, that knew this construction before. In the case of two boundary components, the symmetry argument is not going to work so well. And in general, although these boundaries are umbilic, you cannot be mapping both of them. If it's injective, you cannot be mapping both of them into a hemisphere. So the idea that you have to use here is you have to change the metric. So there's one more element with two boundary components. You have to change the metric using what is called Escobar's problem, that is the Yamabe problem with boundary. So the first thing that you do is change the metric to what is called the Escobar's metric, or some people know it like that. So let me tell you what is this metric. The problem that he posed, actually he posed many variants of this problem. One of the problems that he studied is trying to find constant scalar curvature and zero mean curvature at the boundary. And under the conditions of our theorem, or actually more general conditions, but in particular in the conditions of our theorem, he showed that you have a solution for that you can find a metric that has constant scalar curvature, but zero mean curvature at the boundary. I don't care too much about the curvature inside, but I do care about the curvature at the boundary, because that means that when you do the doubling, the metric that you're going to get is a metric that is smooth through the boundary. Then you can use the developing map and the results of Shen Yao to show that, in fact, you will have something that maps into a fundamental domain. You still could have branching points in principle, but at least you're going to be injective. So the thing that you need to rule out after that are the branching points. And then comes the last condition that I put in my theorem, that is the Q curvature has to be positive. The Q curvature being positive, there's a result by Shang, Han, and Yang, Alice Chang and Paul Yang and Han, that they show that when you have Q curvature positive, then you cannot have those branching points. So the three elements are there in this proof to show that you in fact have an injective developing map is that you have a Escobar's metric to be able to double and have smooth metric. Then you can use Shen Yao to show that you're gonna have an injective map. And then the Q curvature shows you that you don't have any branching points. So basically you're mapping into something injectively where the two boundaries have to be umbilic. So if you are mapping on the sphere, these two boundaries have to be not great circles, but circles on the sphere. And this is gonna be an annulus. And then by a stereographic projection, you can take it to an annulus in R4. That is where we did actually our explicit computations. We have explicit numbers for the bound. In the theorem, we didn't write them because they were not very nice. But, and we don't know which one of them is the smaller. We have a series of numbers there. And that's sort of what we use to conclude the last part of the results. So once you have the mapping, you use the coordinates. The coordinates are not going to be the test functions, but you can use them to construct the test functions that are basically the same that we found doing explicit computations. I mean, we could write our functions in terms of these coordinates that we had before, and that's what we do in the last part of the theorem to get the actual bounds. There's a step in between that I'm skipping, and because I'm running out of time, I'm not going to go into detail. That in this case, it's not known that the operator, that Paneitz was not known that Paneitz is positive, so you have to show, or that the B3 is positive, so you have to show in these explicit computations that you're going to get actually also a lower bound. But this is more or less direct because you have this mapping into these models where the energy is much simpler. I mean, you're in Rn, so you don't have all the curvature terms. You only have basically a bi-Laplacian square, and that's positive. So the positivity actually follows because in the standard models, the energy basically only has the first term. I mean, this is the other energy, but my energy here only has the first term. So that's how we know that it's positive. But you have to show that also in the and show that this sort of carries to the model as well. And yeah, and I'm gonna stop here. Thank you.
Thank you very much, Mariel, for this nice talk. And we have time for questions now. So please just unmute yourself and go ahead if you have a question.
I have questions, but I don't want to hog time if someone else wants to ask something.
I have a question just to come back to what I asked. You said it's possible that the operator is not bounded below. When you said that, I think I see that quite clearly for the boundary operator, but did you say that also the Paneitz operator itself could be unbounded below?
I think it can also be unbounded below. I'm not completely sure, but I have the impression that in general, you don't have a lower bound.
Okay. Thank you.
I mean, in the general case, you can have more terms, but in the four-dimensional setting, actually, maybe you know more. Yeah.
Okay, thanks. And do you know if it's easy to construct an example where you would see that it's not bounded below, or like a geometry where you see that the operator is unbounded?
I can actually answer. I mean, the Paneitz operator itself is definitely bounded below.
Ah, okay.
It can have arbitrarily small, I mean, arbitrarily negative eigenvalue, but for each given metric, it is bounded below because it's a compact perturbation of a bounded below operator.
Okay.
A relatively compact perturbation of.
Yeah. Okay.
Yeah.
Okay. But so for the boundary operator, it might be different because you could have the rest of the terms compensating.
Yeah.
Okay. Thanks. So I think Misha, you had other questions.
Right. So the main question is that so you started your motivation talking about surfaces.
Yeah.
And for surfaces, so of course you can consider bounds for all metrics, but people also consider bounds in the fixed conformal class, and that's also a meaningful problem.
Yeah, exactly. Yeah.
Right. And so as far as I can see, what you're doing is basically you cannot quite get so I think your results are just results on the conformal class, right? So they could be stated as if you fix the conformal class of a round sphere,
That's
then
right.
you have this.
That's right. And somehow, I mean, our goal at the beginning was try to have a more clear connection with with the topology somehow. I mean, see maybe the Euler characteristic or something, but we couldn't get anything in that direction. So yeah, we're fixing at the end, yes, we're fixing a conformal class. Yeah.
Yeah, but you do a bit more because you say, given this characterization geometrically, this is the conformal class that you get, but
yeah, but I mean, the restrictions in some sense give you that. I mean, at the end, yeah.
Okay.
It's a complicated way of fixing the conformal class at the end, yeah.
All right, so and going back to my question on like minimal surfaces, et cetera. So similarly, if you fix the conformal class, right, then for surfaces, then the critical points of the eigenvalues give you the harmonic maps, right, which are critical points of energy. So have you tried to do this computation here, where if you fix a conformal class, what are the critical points for eigenvalues, and are they the?
Yeah, no, I haven't, but I think it's a very good question. I mean, we were for a long time trying to think about something like this to compute. We tried some things, but this in particular, I haven't tried. So It's a good idea.
So if you want my guess, then you should get the critical points of exactly that energy that we were talking about before.
Yeah.
And so that's why I was curious if that energy is something that people considered before.
but
Because this
it's
is the conformally invariant energy, right? So if you change the metric, energy will stay the same.
Yeah.
And the Paneitz operator is conformally covariant in the same way as Laplacian is, right? You get just e to the minus 4f in front and nothing inside.
Yes.
My guess is that you should get exactly what I'm saying, but
you could be right. I mean, you could be right. I mean, this is kind of what we were looking for at some point, but we couldn't maybe find the correct thing to look at. I mean, I think that's something that we were missing at some point.
Yeah, so I think that's something worth looking at, especially if people looked at something like this before, at that energy, if that's something interesting for people.
Check that.
So Misha, in dimension 2, what you get is conditions that give minimal surfaces. So do you also have a guess to what the geometric characterization would be in this case? Or because you don't know the energy?
Yeah, so for conformal, right? So for conformal class, you get the critical points of energy. If you want my naive guess, for critical points in space of all metrics, you get conformal objects, which are critical for energy. The critical points of energy plus conformality, but maybe something else, because for the problem, you could get something a bit more than that. But the naive guess is that it's the same object is in conformal class plus condition of being conformal.
There's definitely also the fact that just getting the existence of anything maximal for fourth order problems is orders of magnitude harder than getting the existence of the critical points for second order, because there's
but I agree, but here we're not really talking about the existence of maximizers, right? I'm just talking about what is the condition for it to be critical. Just
yeah.
And
but the lack of maximal principles really hurts you for.
Probably, yeah. Well, the existence question probably much harder than it is in the surfaces. But
Thank you for the questions. I guess I'm thanking myself. That's strange. Anyone else wants to ask something or comment on something? I guess I have a very naive question. Do you know if there's a physical interpretation to these in this context, in this more geometrically evolved context?
It's a very good question. I don't know. My answer is I don't know.
Yeah, I really don't know either. It's anyone else wants to ask or say something? No. Thank you very much, Mariel, for this very nice talk.
Well, thank you very much to all your comments.